Let's continue our discussion of dielectrics, and we'll talk a little bit more about bound charges. If we look at the field inside of a polarized dielectric, one might ask, what kind of dipoles are we actually talking about? You remember there's pure dipoles and there's physical dipoles, so that's Q times D. There's a physical D that's involved here. Here we've let the D go to 0 to keep the dipole moment constant. Well, outside the dielectric, there's really no problem. You can take either one of these. We've shown before that if you take the polarization, capital P, in the dielectric, multiply by a volume of a sphere, you'll get a dipole moment associated with that volume. Well, that works pretty good as long as we're far away from these little units, the little volume elements that make up the dielectric. So d taus that make up the dielectric. Inside the dielectric, however, we have to be careful about these dipoles. We can't pretend that we're far away because we're wandering through high densities of these dipoles. So if we were to try to examine the microscopic field, it would fluctuate dramatically because you've got tons of point charges, and so that's going to drive you crazy. So what we do is we average. We average over some small volume. So in other words, we've defined capital P, and this averaging smooths out the microscopic fluctuations. This average is what we mean by the macroscopic field inside. Since P, the polarization, is averaged, the E field inside for a uniformly polarized sphere is equal to this quantity here. It's equal to minus P0 over 3 epsilon naught in the z direction, where the uniform polarization is in the plus z direction. So this is the average value of E. So that's the E inside, or what we call the E local field, and this is the correct magnitude of that field, and of course it's opposite to the polarization, so that's why there's a minus sign here. For parallel plates, we also looked at the E field inside, and that's equal to E local, and that was equal to the applied field, E0, minus the polarization over epsilon naught. So remember, this decreases, so the dielectric acts like a shield. So going back to our parallel plate system, we have this dielectric that's placed between parallel plates, and we've applied a battery or potential such that we have positive charge on this plate and negative charge on this plate, and the dielectric polarizes. So if you remember, the dipoles would be induced in this direction here, and every dipole has a mate here, so that the net result is there's no bound charge inside of the dielectric. However, here you'd have a dipole with its tail sticking out, and here you'd have a dipole with its head sticking out. So that gives you this plus bound charge, and this gives you the minus bound charge. So if you look at the field due to those net surface charges, that gives you an E field in this direction, and that's what we call the E bound. So the local field is the difference between those, so it's E0 minus E bound, and that'll be the E local or the E inside. So if we start here with the definition of sigma b in terms of the polarization, it came out that it was the normal vector to the surface dot p. Well, because p is parallel to the z-axis, or this direction here, then we know that the two parallel surfaces of uniform charge density will be plus minus sigma b. In other words, they'll be equal in magnitude. So that's what we said. The E bound is going to be the surface charge density, the bound charge divided by epsilon 0. E0 is E0 x hat. Then E bound will be equal to minus sigma b over epsilon naught x hat. But if we go up here, sigma b is equal to p, and so we would have then that the E bound is minus p over epsilon naught. It's minus, of course, because the induced charge, the bound charge, would create a field in this direction. So this is the field due to all the surrounding dipoles, which end up only affecting the surface. There is no bound charge inside. So this average electric field that points opposite to the direction of the dipoles themselves, the E-bound, that will give you then a way to get the local charge. So we take the E inside, E local, to be the applied field minus capital P over epsilon naught. So again we see shielding of the E0 from the bulk of the material. So normally this would not be large enough to totally cancel this. So your E local would be smaller than E0, but not 0. So let's ask the question, what if we replace the dielectric, which is an insulator, with a big block of metal? So we want to make sure it's insulated from the plate so we can apply the charges on the outside here. So pretend now that this is a metal, and so let's ask what happens. Well, first of all, we establish again the plus minus sigma free, and let's pretend that we do this instantaneously. So this is for drama's sake. So what happens is that the electrons in the metal will flow quickly, as fast as they can, until the E inside is equal to 0. Remember, otherwise free charge will continue to flow until you get that field to 0. So what happens then is that you leave positive charge behind, and then here's the negative charge, the electrons, which ended up on this surface here. Well, we have to have the E0 due to the free charge equaling this sigma free over epsilon naught. This is not 0. However, if we look at the bound charge, in order to get the E field inside to be 0, we would have to have equal sigma B and sigma F with the opposite sign. So this is plus minus sigma B, this is minus plus sigma F. So the E bound then will give us the cancellation. So we'll have minus E0 because of the surface charge. So what I'm saying here is that if we did a Gaussian surface, a pillbox like this, so this is in the metal, this is in the metal that we pretend is a dielectric. So if the E field here is 0, remember it's 0 over here, then this charge density has to be equal and opposite in magnitude to this charge density here. So that's what we mean by this relationship here. So we have then the equality of the magnitude with the opposite sign. So doing that then, we add up the E bound with the minus sign with the E0, and we get 0 field. So this would be the local or E field inside. So we have total shielding. So sometimes we refer to metals as being perfect dielectrics, and we'll learn that this corresponds to an infinite dielectric constant. So note that there's no induced dipoles inside the metal. Sigma B is strictly due to the free charge on the metal surface. Is this useful? Well, not really, but it is an illustration of what happens as you allow more and more charge to separate in the material. Well, let's look at an example of a dielectric cube that is of side S, centered at the origin, and it has a frozen in polarization. So capital P is K times R. K is just a constant. So our job is to find all the bound charges, and then when we have those, we can check that they add up to 0. So here's our cube, side S. Here's our R vector relative to the origin right here. And theta is defined, of course, the angle between the z-axis and the R vector. Well, notice at the surface then we have the polarization headed in this direction. We have the unit vector normal to the surface headed in this direction. So obviously the projection of P onto N is going to be related to the surface charge density on this surface here. There's no free charge, and the bound volume charge, which we called rho sub b, is equal to the divergence of P with a minus sign. So this is the equation we derived for the rho sub b. Well, we're in spherical coordinates, so let's just take the divergence, which equals this quantity here, operating on kr, and the minus sign is this minus sign right here. So taking all the derivatives, we end up with minus 1 over r squared, 3k r squared, the r squares cancel, and we end up with a constant charge density inside. So it's just a number, it's a scalar, and everywhere inside it's the same value. Since the bound charge is constant, then the total bound charge will be equal to the volume of the cube times the charge density. And so this would be the Q inside the volume, this would be the bound charge inside, is equal to rho sub b times the volume. Well, the volume is just s cubed, and so the total charge inside is minus 3k s cubed, and that's the bound charge. How about the surface? Well, we go to our definition, the equation for sigma b. This is the bound surface charge density. It's equal to capital P dot n, so that'll be kr dot n hat. But look at r dot n hat, that's equal to r cosine theta. And if you look at your picture here, if you take r here and theta here, it's equal to this distance right here, and that's s over 2. So we can set that dot product equal to 1/2 s. So now if we take the surface charge density to be this quantity here, what we find is that it's constant. It does not depend on r and theta along the surface. So we have a constant sigma b, and so everywhere on the surface of this cube it's a constant sigma b. So this holds for any point on the surface. So any of the 6 sides of the cube will give us this charge density. So in order to find the charge, we'll take this charge density and we'll simply multiply by the surface area of the cube, and so that'll give us the total surface charge on the cube. So when we do that, we'll basically get 6s squared for the area times sigma b, and that gives us plus 3ks cubed. Well, I think you can see now that if we add these two together, so we take the bulk charge, the bound charge, and the surface bound charge, and we get 0. So before polarization we had no free charge and we had 0 total. After polarization the same thing happens. We have Q0 equal to 0. So the next thing we'll talk about is the displacement vector. We call that D. And so we have dum-de-dum-dum with emphasis on the D's. And so now I'd like you to have the children leave the room, and you might want to go to this website.